Good good afternoon. Good afternoon. Oh wow, a lot. All right. Good afternoon. Good. No, actually, wait, hold on. Sorry. Um, no, just wet, a little. No, it's just wet. But thank you. So hard. Oh, wait, hold on. It's there. It's all there. Hold on. Okay. You guys are so prompt. It's so great. I'm a little bit. I think I'm still a little bit. Okay. Uh, Good afternoon, Andrew. Hello and good afternoon, she. Good afternoon, Alyssa. Good afternoon, Vivian. Good afternoon, Nicholas. Good afternoon, Gabriella. Good afternoon, Jay Lynn. You guys will be the first to know if I actually have a haircut or a shave, which I guess is probably in the cards. Good afternoon, Jayla. Good, that thing that means that. Yes. Good afternoon, Michaela. I'm not even sure what that means, but okay. Wait, how am I? Oh my God. Oh, sorry. I think I need a brain cut. Wait, or a brain implant. Wait, I just lost. Sorry. Okay. Um, 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 um. So right. Good afternoon, Stephanie. Good afternoon, Brenda. Oh, I'm not sure that's totally true, private chat. I mean, you're welcome, but I think well, that's not my impression, but okay. I think there was more pleasure than you think. But yeah, they were surprised. But anyway, good afternoon, Catherine with a Y. Good afternoon, Mark with a C. Good afternoon, more two people coming with a admit all button. Okay. Okay, I seem to be a little bit, apparently I'm not firing on all cylinders here. Okay. Good afternoon, Lakshmi. Yes, good afternoon. Oh, you know what's so embarrassing too good afternoon, Celine. Good afternoon. Okay, excellent. Well, there's a big class. We are like all here. That is great. Oh, it's so embarrassing when you see that notification on my screen. That me, my God, whenever. Well, sorry. Can we take those homework down? Can we take them down? Yeah. Wait. Can we take them down? I'm not even sure what that means. Yes. Can we take them down? Wait. I appreciate Nicholas's. Oh. Well, don't worry. I mean, look, I still owe you guys. I mean, obviously, our relationship to homework in this class is a little bit. There's a lot of latitude in the homework relationship in this class, as you know. And by the way, I hope it's clear. Okay. So yes, I did just post 2 homeworks. Yes, they're due next week and the following week. I mean, they're not. It's actually not like bearing down on you. Believe me. Like I'm still giving myself time to turn back yours, but it's also just to keep us moving and to keep you aware of what's going on, and to keep those of you who like to. Anyway, I'm not going to defend the fact that I posted homeworks, but yeah, I posted 2 just so that I wouldn't forget again or something. But the next one is due a week from it's due Monday, like 5 days from now, and then the other one is due a week from that, and the second one, they really could have been. You almost could do them in the opposite order. Almost. It's the second one, just to quickly warn everybody, the second homework that I posted is really kind of an exercise, and we're almost going to end up doing it together in context of class. I mean, by the time you get to that second one, it's almost like a review practice exercise. Like, and I'm not trying to say it's easy, like nothing is easy in life, but by the time you get to that second one, or many of you could even look at it first if you felt like it, and if you're getting what's going on in class and stuff, you won't find that one to be a major. It's not a step in a new direction. It's a practice. The second one, okay, which is technically homework 3. Homework 2 that I posted to be due this Monday. Granted, that is more long and involved. That is like a bunch of math things that we kind of need for this class, many of which we've been doing together, like this calculus stuff, but then some other little pieces that we haven't done. So that other one's a little longer and involved. It's also technically practice. like some of you will find that some of the exercises at the beginning of, I'm talking about now, homework 3, the one I just posted, the one that's due this Monday. And again, and you do it at your own, you do it at your own pace. You do it again. You recognize that I'm grading at my own pace, etc. But for that homework 3, when you want to look at it, it's like the underlying math underneath the physics that we kind of need here. It seems like a long assignment. It is a little bit long because there's different parts to it. But I'm also going to warn you right now, it deals with differentials and equations and then cosines and stuff like that. But then the very last section of it is about vectors, about vector multiplication. We do need that for this class, but we don't need it right now. And all the math is just put together in this one packet. So if you were to attempt homework 3 and give it your best shot, or but if you were to not worry about the vector part of it for next week, that would be fine. I mean, as long as you eventually do it when we need it, for whatever it's worth. So this is not really the answer Nicholas was looking for. Plus, he was sort of joking, but yes, there's a homework that's due Monday. I think you should do it. I think, especially by the time you sit to do it, you'll see that it's more like reviewing what we've been doing rather than a push ahead. The way, the homework 1 asked you to think through all these things before we talked about them. Homework 2 is not quite like that. Neither is homework 3, for whatever it's worth. And I still owe you stuff. So, okay. So that's the deal with homework. Wait. Oh, yeah. You definitely. Oh, no, but you do. Now, wait, that's a great question of Nicholas's, and we'll start in a moment. You definitely do want to do the 5-step process for it. Believe me, it applies. I think I see why he's asking this. The 5-step process does apply to the, it's a good question, but the 5-step method for solving problems in physics, I absolutely do think applies to both of those homework sheets. The reason Nicholas is asking, I believe, is yes, the second homework, the one that is called homework 3, the one that's called a heat harmonic, or both of them have elements that are a little bit exercisey. And I think that's why Nicholas is asking. Like, both of them have certain questions that you might think you could, especially if you are confident and you sort of have been following class. There are certain questions there where you might think, I can do this like in one step in my head. Like, I know the answer. I can see the answer. That's okay. That's all the more reason to do the 5-step process. Honestly, I mean, I don't want to get myself all in a dither here, but like, the 5-step process is a method for you to break apart thoughts that occur in your brain, sometimes very quickly. Like, the easier something seems to be, all the more reason to write it out as a 5-step thing. Again, because that's why when you get to something that doesn't seem easy, or when you get to something that you can't see the end right when you begin, that's where the 5-step method, having practiced it and having gotten to know it, that's when it really does work for you. So I think this is why Nicholas said that. Yes, some of those questions might be, if you find, anytime you're sitting there finding, if you're ever looking at a homework question or an exam question, you're like, I get this. Like, I don't even see how to do the 5-step method. That's great. That means you get it. You're psyched. Like, pat yourself on the back and be happy. But then just put in the little bit of extra time of just breaking your insight into those steps. I mean, remember, one of the steps is just like write down the question. So it's not. So anyway, I think that's what he's asking. But yes, please do. And if there's a word question that's about English or something, okay, I mean, when you really can't do it, don't do it. But I think it does apply mostly. Oh, sorry. Oh, okay. And someone, so no, it was a good question, Nicholas. I think my answer still applies. I think, because those mathematical questions are still these type of questions, even if they're a little bit exercisey. I think. I mean, again, wherever I'm wrong. But I think mostly that's my answer. Okay. And we may be temporarily interrupted in a moment. For a moment, I apologize. Let me just get this thing going. Okay. So, but we're going to get back to, so we're actually starting to cover some math and physics here, I think, in this class, which is nice. Okay, so hold on, quick, 1 second, please. Um, uh, okay. Um, I'm pausing. Okay, I'm pausing because for sure, believe me, I do want to break for a moment and hear a little bit and discuss a little bit your lab yesterday. I do, but I'm not going to do that just yet. I want to make a little tracks with the material first, material that does link to what we were doing Monday, but also links to what you did in the lab yesterday. So have faith. I know we need a moment. I want to have a little post-op with you, believe me, about the lab yesterday. But I know if I start that right now, we're never going to stop. So if you're dying to say things about the lab experience, good, bad, whatever, you will have an opportunity, all of you, I assure you. But bear with me. I'm going to just get the physics wheels turning first, or the math wheels turning. So, okay. Sorry. I'll get that in a second. Okay, someone's here. Sorry. Okay. In a way, I just wrote a lot. In a way, I wrote nothing new. In a way, I just tried to summarize like everything we're saying so far, the whole point of all of homework one and all of this. So in a way, forgive me, what I'm about to summarize, for many of you in the room, you'll feel like we've heard this 100 times. Okay. And for some of you in the room, you're going to feel like, yeah, I keep hearing it and I still don't know what he's talking about. But I'm going to say it anyway. And by the way, well, there's no by the way. Okay. And some of you may feel, actually, some of you may feel when I say what I'm about to say, you might feel, wait, I feel like he keeps being about to say something that I'm about to understand. And I feel like he keeps saying something on this topic, but every time I'm just about to get it, he changes, it seems like he changes it a little bit and it's a little bit different from the last time. Just when I'm about to get it, it becomes this new thing. If you're feeling that, by the way, then you're definitely in the class. Then you're definitely getting, because that is what's happened. That is, and it's one of the reasons that I say things over and over again is I actually am, to some extent, deliberately trying to say them slightly differently each time, because we are taking a point and molding it and molding it and molding it and making the point bigger and bigger and bigger, or more and more general, or more mathematical, or more universal. Like, honestly, if you ever feel like you think I'm continuing to say the same thing, but it's like never quite clear enough for you to fully grasp, then you're doing physics, because that is what is happening. But anyway, so what I'm saying is this is what I think is the summary, the takeaway of homework one, and indeed an underlying thing that I think was at least half of what was happening in your lab yesterday, and only half of what was happening in your lab yesterday. And we'll get to that. But what I think we're saying here is, like, we started in homework one with a specific mass on a specific spring, like a chunk of material on a coiled piece of metal, going back and forth along a specific x-axis, like a horizontal, like meter stick, right? And we looked at its vibrations or its oscillations, its cycles back and forth, and like did all this math and did all this analysis and came to a certain conclusion about the value of x. In that case of homework one, we came to mathematical conclusions about what was happening to the value of x as time ticked on. Okay, now, and we said a bunch of things about x, like we said differential equations, we said solutions. Now I'm deliberately, I think for maybe the second time, not the first, but for the second, I'm deliberately now, instead of writing x, I'm writing z. Okay, that is a slight change. That is on purpose. I'm trying to do two things when I change this to z now. First of all, and by z, I mean it to stand for any measurable dependent variable that you can imagine, or that you could literally measure. Like z could stand for x, or z could stand for x along the z-axis. It could mean that, but I don't only mean, or it could mean x along this axis. But I want to be even more general than that. Like, you can make up your own squiggly symbol if you want. I want you to picture that z could stand for like angular position on a pendulum, or z could stand for temperature, as it will in homework 3, which was just posted and due in 2 weeks. Okay, z could stand for any quantity that you could imagine measuring, which seems to be varying in time, something that you're measuring while the clock ticks. Okay, so z is now any general measurable dependent variable depending on time. What we're saying from now on, like the conclusion we're coming to, is if we have any reason, mathematical, theoretical, experimental, we have any reason to believe that that differential equation, that second order differential equation, d2z dt squared equals negative omega squared z, if we believe that that equation describes the behavior of these z values, right? And I mean the z, like the behavior of the values. Like if we made a table of values of all these temperatures or all these electric field magnitudes or whatever, we charted them out and we watched and we saw that those values could be plugged in and satisfy this differential equation, then we know something, we immediately automatically know something very important about how z varies in time. And what we know is that cosine equation written at the bottom of the page. Let me pause for a second and say, the thing that, again, some of you may think I'm saying over and over again, and you're right. And some of you may think, yeah, I don't care how many times he says, I tune out every time he says it because I don't like it. What I'm saying here is, when I say, if we have reason to believe that Z satisfies D2Z dt squared equals negative omega squared Z, when I write that, please understand that by omega in that context, by omega squared in that constant, in that context, by omega squared, think of omega squared as a symbol unto itself. Think of omega squared as a clump, or what do you, I think that's the word, clump or a lump, or a, I think it's called a clump. Like, it's just a thing. Omega squared, it's a symbol that stands for some positive constant. Constant meaning it doesn't change. It's not a variable. I know it looks like a variable because it's like a Greek letter and everything. And it looks even more like a variable to the unconscious mind because it's being squared. So it makes everybody think, oh, is this some sort of like quadratic equation? Is it like a parabola or something? No, no, no. Please, 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 no. Omega squared is just a symbol for some number that, honestly, really, it's a symbol of some number squared. But a number squared is just a number. So imagine, so if omega squared is any number, like 25, 36, 712, and then omega squared just stands for that number. And what we're really just saying, it's shorthand for saying, imagine that we have reason to believe that the second time derivative of some variable is directly proportional to the variable itself, right? That's really what we're saying, because to be directly proportional to something means equal to it times a constant, right? So we're just saying omega squared just stands for some constant. We could have called it beta. We could have called it C. But why are we going through this extra, like this weird thing of calling it something squared? Like, why are we doing that? Because what we have found by doing our math, by solving or by conjecturing and verifying and taking derivatives and yada, yada, what we have found is that any variable Z that can be described by this differential equation, D2Z d squared equals negative omega squared Z, is a variable, is a measurement, is a number that is oscillating harmonically. Okay, so anything that's described by that differential equation is a value that is, in fact, going up and down in time, or, you know, is getting increasing and decreasing in time in that smooth back and forth, regular, predictable, cyclical way, so nicely captured by cosine functions. Okay, so we're saying if you know that differential equation is true, then you automatically know that the Z measurement is oscillating cosinusoidally, right? And more specific, and so you can just, you know, that Z equals Z naught cosine omega t, right? And because we've tested already that if you differentiate that twice, you get back the original. We tested it with X's, but what we're saying is in math, like, it doesn't matter whether you call it X or Y or P, like what happens to the variable would happen to any variable, right? So if you have that differential equation, you know that the equation of motion for that value, like even if you don't literally see motion through space and time, even if that value stands for something like temperature, I'm saying, then you know that that value is cosinusoidally oscillating. And now I go a step further and I say, yeah, it's going back and forth and back and forth, but it's going back and forth in a way that is so regular and so patterned, so reliable, so constant that we call it harmonic. What does harmonic really mean? It means that the cycling rate, and you might want to write this down somewhere. Like when I say harmonic, I mean, so this whole thing is what simple harmonic oscillation really means in general. A value will harmonically oscillate if it can be described by that differential equation. Like that's, and that differential equation secretly is really just Hooke's law, right? We're just saying if there's a linear restoring force acting on some measurement, then the measurement will oscillate harmonically. But now what I'm saying further is what does it mean to oscillate harmonically? Like, what's so special about harmonic oscillation? What makes it different from any ordinary spazzy oscillation? This is the part to write down. Harmonic oscillation means that the cycling rate of oscillation, the oscillation rate itself, whether you want to call that angular frequency or you want to relate it back to standard frequency in hertz, or you want to think of it in terms of its inverse period, any one of those three things is equivalent. Something that oscillates harmonically oscillates at a rate, a cycling rate, which is, okay, this is the part to write down. So maybe I should write it. Yeah, wait, I'm going to write it on the next page and then I'm going to come back. Okay, what I'm saying here, then I'll go back to that page again, but I'm saying harmonic oscillation it comes about whenever that differential equation is true, whenever Hooke's law is applying to a system. What it means to harmonically oscillate, it means to oscillate very steadily. Yes, I mean, in simple terms, to oscillate harmonically is to oscillate very steadily, but the steadiness is very specific. It's actually quite phenomenal. By steady oscillation, by harmonic oscillation, we mean, number one, yes, that the rate of oscillation, the cycling rate, is a constant. Okay, the constant that describes that most mathematically directly is omega, the angular frequency, right? And I was trying to emphasize 2 days ago and sort of last week that angular frequency is your cycling rate, only it's measuring in radians per second rather than in cycles per second. And a radian is a sixth of a cycle. Okay, so omega is really how many sixths of a cycle you're making per second. So you can then, and why do I say 6 again? Because 6 is basically 2 pi. So angular frequency is what comes directly out of the math. If you want to make it more intuitive in your mind, as we all do, you can take a cycling rate and divide it by 2 pi by 6 and say, oh, that's your standard frequency. And again, okay, I'm going, but just to remind you again, if someone says, I've got an oscillator here with an angular frequency with an omega of 4 pi radians per second, to all of us, that sounds very abstract and removed from reality. To all of us, if I hear 4 pi radians per second, my brain doesn't immediately go, oh yeah, I can picture that. No, nobody, I mean, maybe it sort of does, but not really. If you say to me, omega equals 4 pi radians per second, what I say to myself is, oh, there's 2 pi radians in every cycle. So I divide by 2 pi in my mind. I say, oh, she told me omega is 4 pi radians per second. I divide by 2 pi radians per cycle. And I say, oh, so it's doing 2 cycles per second. That's what you're telling me. Okay. So I go from in my mind from omega to F. Then I can even go one step further and go, oh, it's doing 2 cycles per second, i.e. 2 hertz. That's how rapid the oscillation is. Oh, I can flip that in my mind and say, oh, then I guess it has a period of 1/2 second every cycle, right? Okay, again, I'm a little bit off page here, but I'm just reminding everybody that omega, F, and capital T, F as in standard frequency, omega, F, and capital T are 3 interchangeable, mutually locked, interdependent, 3 equivalent ways of describing the same constant, the same thing, which is cycling rate. Omega is the most mathematically direct, most mathematically useful, and therefore the most abstract. T is the most easily picturable in the mind, the most experimentally measurable. And F, standard frequency, is like the bridge between the two. If you ever can picture one, you can get the other two. All of them are just ways of talking about cycling rate. And cycling rate is hugely important to us because now back to this page here, I'm saying that anything that oscillates harmonically is oscillating at a cycling rate, is cycling at a rate that is, first of all, steady. It's constant. We call that constant omega. But second of all, B here in the middle of the page, what's really powerful and deep about this, it's going to come up more and more as we more and more talk about waves, which was the purpose of your lab yesterday. The really key thing about omega is, notice, omega doesn't depend in any way on what you might call X naught, or you might call Z naught, or you might call capital A. Omega, the rate of cycling in time, does not depend on or get determined by or even relate to amplitude, the maximum displacement or the initial displacement from equilibrium. In other words, what's really interesting about a harmonic oscillator, and this will come up again and again, is that it'll go back and forth in time at some rate that has nothing to do with how we set it up in space. Let me just say that a little bit more slowly, or like, and I will keep saying it again and again, but I'm saying whether you're talking about a mass on a spring or you're talking about a pendulum on a string or anything, that omega number, that radians per second characteristic constant is so constant. How constant is it? It's so constant that I don't care whether you set, if you set up our mass on a spring at, if you release it from 15 centimeters away from the equilibrium and let it go wah, 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 and you find, by doing the square root of K over M, you find that it's going like wah, 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 like 3 times a second, let's say, or 6 pi radians per second, however you want to say. If it's going like 3 times per second, or in other words, it's taking 1/3 of a second to go there and back, then you stop. If you take that same mass and that same spring and set it up instead all the way from 45 centimeters, instead of 15 centimeters, right? If you change its amplitude, its X naught, its initial and maximum displacement from equilibrium, if you set it up all the way at 45 centimeters instead of 15, so now you're asking it to go like wah, 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 right? If you do that, what I'm telling you, what this, all this math is telling you, what we're telling ourselves, whether we realize it or not, is that that mass now with that much huger amplitude, with that totally different initial configuration, it's got to do these huge trips now as compared to the small ones that the other guy had to do. It's got to do these huge trips, but somehow, because it's making these huge trips, each trip it's going to start with a lot more potential energy than the little guy did. Therefore, on average, it's going to have a lot more kinetic energy than the little guy did. So on average, it's going to go a lot faster through these trips than the little one did. And apparently, all that math works out perfectly so that the 45 centimeter mass will actually do each oscillation in the exact same amount of time as the 15 centimeter mass. What? Wait, what? Yes, that's what I'm saying. I'm saying I don't care what we do to amplitude. I don't care how big we ask these oscillations to be in space. They're always going to be the same amount in time. Bigger swings will be faster swings by exactly the right amount to compensate and make omega a constant, how like so constant that it's independent of X naught or A. It's an independent constant. It is fixed. Omega is fixed entirely by parameters. It's fixed, it's determined by the ingredients of the system, such as with the mass on the spring, we found that omega was the square root of K over M. And I said over and over, that's very interesting. That's true of a mass on a spring. Don't memorize it because it won't be true. It won't be square root of K over M for like a bob on a pendulum. But whatever system you choose, omega will be determined by ingredients of that system, material properties, which we call parameters of that system, like K over M or L over G or something. It won't be determined by how you set up the system. It will only be determined by the ingredients of the system. Angular free, so in some, and I'll go back to the page, in some I'm saying what it means to oscillate harmonically is that you're oscillating at a rate that is so constant in time, it's not even affected by how you're set up in space. A harmonic oscillator, if you're really following me, then I'm saying a harmonic oscillator is a true, essential clock. A harmonic oscillator is a metronome. It's something that keeps time regardless of space. All clocks of any kind, mechanical, digital, they're all made of either a spring or a pendulum or an electronic circuit that obeys Hooke's law. Anything that keeps time, anything that's a clock, is fundamentally a harmonic oscillator first and foremost. I don't know if that puts any perspective into it, but anyway. So now going back a page a second, mathematically, so that's what we're dealing with here is harmonic oscillation, and also just to try to keep every little piece of your long string that you looked at yesterday, every little chunk, every little X value that you made red dots on and that you looked at, each one of those, if you found that each one of those pieces, when you held X constant and you measured Y as a function of T, you found out that every one of those little pieces of the long spring was itself a little vertical oscillator, right? That means it was going up and down at a rate that was not determined by anything but how springy that spring was. So omega is like really important. Omega is the way to describe an oscillator. It is the constant that characterizes the steadiness of oscillation. And what I'm saying on this page, and then I'll move on again. And again, I don't even know whether I'm like technically reviewing right now or saying something new to anybody, but I'm saying that if something is described by that differential equation at the top of the page, I mean, in the middle of the page, then it oscillates cosinusoidally with a rate, with this steady, constant angular frequency rate measured in radians per second. And what I'm saying is that rate is always automatically necessarily the square root of whatever the constant of proportionality is in the differential equation. That's why we write. So this is, again, it's kind of all in the spirit of reverse engineering or retrofitting or Monday morning quarterback, whatever you want to call it. Like it is, this is all a little bit like backwards thinking. That's why I kind of have to say it over and over again, because it's a little bit unusual until you get used to it. That the reason we write the constant of proportionality in the differential equation as omega squared, the reason we write it in this weird way, like as a square, even though it's just a number, is because we're anticipating, we're saying, whatever that constant is, we know that the dependent variable will oscillate cosinusoidally at a rate which will just automatically be the square root of that constant. Like, because chain rule brings out the constant twice. Like, so from here on in, we don't have to keep resolving this differential equation. If we ever see it, we just know the solution is variable equals variable naught times cosine of omega t, where omega measured in radians per second is literally just the square root of whatever was the proportionality constant. Okay, that's what we're saying from now on. That's the sum of what we were saying up until Monday. That if we have so this is harmonic oscillation captured. The definition, the defining constraint on harmonic oscillation is that differential equation. The solution to that differential equation is, or this solution is, an equation of motion that describes each oscillator. Okay, I'm gonna pause for 1 second. Now I want to move on. I want to start relating this more and more to your lab yesterday. And believe me, again, I really do want to. Believe me, I want to pause as a human being and sort of as human beings post-op the lab yesterday. But I'm a little bit concerned about the material too. So forgive me. But we will. You will. I mean, we will. Even if we don't get to it today, I would. I mean, I've heard great things about you guys. I'll just say that he was very excited about you guys, and obviously. Okay, I don't want to get into that now, but I've heard great things about you guys. I want to hear you about him. Obviously, this is all very unusual that you started with a new person in the middle of the semester. You know, everybody has to adjust to that. But from anything I've heard so far, I'm very pleased with how welcoming you guys are being to him and how welcoming he's being to you. And he was very pleased with your performance. I'll just say that it was. And I know there were glitches about not having lab handouts and stuff, and that was actually totally my fault, as you can imagine. And I apologize for that. And I guess I'll just say this too. I know that in more ways than one, I mean, I've now heard from both sides, from some of you, that I don't even know how to say this, but I understand there were surprises in both directions, that he didn't look like what people were picturing that he would look like. I don't know if, I mean, maybe because Joe and I look so weirdly, maybe you think I don't know what that's all about, but yeah, no. I mean, but I'm saying this lightly to everybody. Look, I'm saying he might have looked younger than you might have expected. And he knows that, and you know that he knows that. But it sounds to me, and I've gotten this from both sides, I've heard from both of you, in some case, not all of you, but that there was mutual. But it sounds like everybody just totally was like, oh, ha ha ha, oh, surprise me, oh, I didn't see, which is fine. We're human beings. Honestly, I don't think there was offense in any direction. Maybe I'm offending people right now, and I don't mean to be, but I think it's all good spirited, and I think it was pretty clear. I post-opted with him afterwards. Pretty clear to me that he felt that your spirits were totally enthusiastic, and that your substance was totally there, that you were there to learn, and that you learned. That's his. And I still do want to hear from you guys delicately, but I'm just saying. I've been doing this for a long time, people. I've experienced a lot of first day of classes, like conventional first day of classes. I've experienced a lot of new professor, new group. I've even experienced some oops, middle of the year having to do this, always awkward. And these things can be train wrecks. I mean, I hope you all understand that. The first day in a new lab with anybody can be a train wreck. The first day in a lab in the middle of a semester can be a train wreck. The first day in the middle of a semester when we haven't even been in the lab for 2 years and we all have a disease and a mask and a this and a that, train wreck potential. Yesterday, maybe my standards, I don't know, maybe it's about managing expectations, but people, let me just tell you, because I'm getting some stuff in the direct chat here. Let me tell you, a lot could have gone a lot wronger yesterday in both directions. He could have been a lot worse, and you could have been a lot worse, and blah, 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 blah. It could have fallen apart. My impression is that is not the case. And I'm here to commend you guys and commend him that I think we're all doing good stuff under challenging circumstances. And if you think I say that crap all the time, maybe I do for 2 reasons. 1, the circumstances are challenging. 2, I think you're a very good group. 3, I think we all need to have I'd rather maintain that perspective in general than the opposite perspective, believe me, which I've tried. It doesn't work. Let's all stay positive is basically what I'm saying. And if I sound defensive right now, it's because I'm seeing things in the direct chat that are making me nervous. Hold on a second. Okay. All right. So fair enough. What Gabrielle is saying that, okay, this is what we're going to do. It's 1 o'clock. I'm going to walk away for a second just to close the door. I guess I've now done it. I totally did not want to do this. I did not want to break the seal, but okay, I've broken the seal. We'll pause for a couple minutes for group station identification, i.e. if you want to let it rip a little bit in one way or the other about in the chat or whatever about yesterday. I'm here to tell you, I think yesterday, what you were set up for challenge. It was set up for things to be tricky and people had to be on their game. I think you guys were on your game. I think he was on his game, and of course, I'm really here also, the material, the substance of the lab. It's not an easy lab under any circumstances, or it's not a obvious, I get it lab under any circumstances. I'm here to still help try to clean up, to refine the ideas we got from the lab. But we could take 2 minutes now. I'm going to walk away for a second. You can let it rip in the chat or say whatever you want just about the lab experience or the human experience, or let it rip for a second, and I'll entertain that because you deserve it. I'll be right back, though. Well, no one is letting everyone. I don't know. Being punked. I mean, wait, so does anybody? I mean, you feel? I mean, okay. I see Gabriella's comment, and I think what she means is, well, and I don't want to get too. I mean, if you're saying he looked a little bit younger than say I do, yes, I mean he is, and also I look older than because I look like I haven't shaved since like the 3rd century BC, and that's also true. But did anybody want to say anything, or have I not? Maybe I've blown there. So, but well, all right, we could just keep. But if you want to say something in the direct chat or the public chat, if you did have any feeling about yesterday, I do want to hear it. I mean, somewhat carefully, but or I don't. But anyway, I think he was very excited to have met you. I'm very excited this is all happening. At least we now have steady stream. All right. So thank you, guys. But yes, if you want to communicate with me in any way, or you have feedback about going forward, please do. Like, it's your class. It's not our class. But oh my God, why am I so okay? So now, physics-wise, also, if there's any physics question about what I'm saying, please stop me, because now I'm going to push it a little bit forward. I am going to push, like, if you follow this is harmonic oscillation. Harmonic oscillation is cosinusoidal oscillation solving that differential equation. Okay, but now I want to sort of like the punchline of your lab yesterday, but I want to unpack it more. The punchline is that there's a way to put oscillations to get oscillations in time together with oscillations in space. And when we do that, we get this new advanced thing called a wave pulse. I mean, that's the punchline. Like, everything we're doing in a lecture right now is about harmonic oscillation. It's about vibration. You took a step into the great beyond in lab yesterday. You built or analyzed or dissected a new phenomenon called a wave pulse. To be clear, that's not anything we've ever said anything about in lecture. I mean, it's not a coincidence. What you did was, whether you know it, you looked at something called a wave pulse and you ripped it apart and found that a wave pulse, it consists of harmonic oscillation ingredients. Okay, for what it's worth, what you're conceptually trying to see yesterday in the lab is that a wave pulse, which is a new thing, an important, exciting thing, that a wave pulse is made up of harmonic oscillations of different types. You, just to be clear, and now I want to show you that from a different angle here now in lecture, but we're not saying that all oscillations are wave pulses. We are definitely not saying that. We are not saying that I have been teaching you about waves in the lecture. I have not. I've been trying to be teaching you about oscillations, harmonic oscillations. A harmonic oscillation is not a wave pulse, and a wave pulse is not a harmonic oscillation, but a wave pulse is a phenomenon that consists of multiple harmonic oscillations. So we're saying that wave pulses are built up from this fundamental ingredient of oscillations. Frankly, where are we ultimately going in this class? Or what am I really excited about in life? I'm excited about wave pulses. I think wave pulses are unbelievably cool. That's what I want to spend like a lot of the rest of the semester talking about. But the way to understand them is that they are a recipe built from the main ingredient known as a harmonic oscillation. And that ingredient is sort of twisted and perturbed in different ways. So that's why in lecture, we're spending so much time talking about harmonic oscillation, because it's the fundamental ingredient behind a wave pulse. Now, let me show you what I mean in a slightly I'm going to show you something that directs our attention back toward that lab thing, but it is from a different perspective. So here we go. And you'll see this in the math methods homework also. Sorry. Okay. So let's consider, I'm going to ask you now, fresh start. Like this relates to a homework problem that's coming up, but you haven't done it yet. This is just so fresh start. Like this is just a new thought to make a new point. So let's consider a somewhat related, but somewhat different cosine function. I'm going to do this one in terms of y's rather than x's. I'm sort of trying to ask you to get used to the fact that it doesn't matter whether we talk about an x or a y or a z or whatever. The important thing is to know what, and it doesn't matter, by the way, sometimes I would call that constant right before the cosine. Sometimes I would call it x naught, right? Sometimes I would call it y naught. But as you might have noticed in the lab, for example, sometimes I might call it A, where A stands for amplitude. And I'll even make that clear with words. Okay. Again, sort of maybe it's a slightly distracting sign, but I'm trying to get everybody used to it. We don't care about particular letters. We should be versatile. We should be dexterous and not care whether something's an X or a Y. We shouldn't care whether something is a Y naught or an A. What matters is whether they are an independent variable, dependent variable, whether they're a constant, a universal constant, a parameter. And so sometimes we use like Y naught, sometimes we use A, just to be clear, capital A. Capital A stands for amplitude. Strictly speaking, amplitude means the maximum displacement from equilibrium, like for any oscillator. Sometimes we use like Y naught when we want to emphasize initial displacement, like Y naught would mean the value of Y when t equals 0. Sometimes we use A. They're emphasizing different facts. Y naught is emphasizing the fact that it's the first value of Y. amplitude is emphasizing that it's the greatest value of y. But what we're saying is for an oscillator, that turns out to be the same thing. Wherever you start the swing is the maximum size of your swing, assuming that when I mean by start, I mean from rest. If that's what we mean by start, like then they're one and the same. They're the maximum potential energy place because it's the minimum kinetic energy place. Okay, so whatever. So let's say I have this function y equals a cosine omega t. That's all old news, but notice now my new thing that I'm throwing in for the next 20 minutes. I'm saying, what if I throw in some term, like some constant term, like pi over 2? And that's just an example. I could have thrown in pi. I could have thrown in pi over 4. I could have just thrown in the number 7. But what if I throw in a term? What am I doing with this term? Or like why? I don't know yet. But let's just assume that this term I'm throwing in. Now, I'm just throwing this in because I want to consider something. Okay, again, I'm starting a new idea. I'm thinking about something. I'm imagining that I throw in this term into the parentheses, and it's just a number. It's some number that's constant. It doesn't have a variable in it or anything like that. And it's a constant that must be measured in radians, whatever this number is. Why? Well, because first of all, it's being added to omega t, and you can't add anything but radians to other radians, right? So it must be. Second of all, if it's in that parentheses and the whole thing is going to be cosigned, then the whole thing has to be in radians. So let's just imagine that I just throw in this number, pi over 2. Okay. Then my question to myself, and I'm asking myself, like, you don't have to, we're not going to stop and have you do this because I'm a little bit pressed for time. But let's say I say, okay, so I'm just going to, based on what we did like last week, I think people are getting more up to speed with this. I'm just going to do this. I'm going to take the derivative. I'm going to take the first derivative with respect to time of a cosine omega t plus pi over 2. Remember, pi over 2 is just a numerical constant. If you want to do this yourself while I'm doing it, see, please do. If you, but so what I'm going to do, the same thing as I did yesterday or Monday, I'm going to do trigonometric derivatives, and I'm going to deploy the chain rule. So I'm going to say dy dt equals negative a omega sine omega t plus pi over 2. In other words, what did I do? I did the same thing. I did trig derivative and I did chain rule. But when I looked at chain rule said, what's the derivative of the inside? The derivative of the inside was merely omega, right? Because technically it's the derivative of the inside is the derivative of omega t plus the derivative of pi over 2, but pi over 2 is a constant. So the derivative of it is 0. This is like, right? If I have a function y equals mx plus b, what's dy dx? What's the slope? What's the derivative of mx plus b? It's just m plus 0 in effect, right? So what came out was just the omega. but then everything stayed in the parentheses like before, right? So that's my derivative of this new function that I'm just testing for whatever reason. Then I take another derivative. Right? Just like yesterday, same deal. Now multiplication is commutative, so I just rearrange things a little bit for a second. And then I go, oh, wait a second now. What have I just shown myself with 14 minutes left? I've just shown myself, hey, hang on. We keep saying over and over that the solution or a solution to the differential equation is a cosine omega t or whatever. What seems to be happening here, what I seem to be discovering here is that even if I throw something into the parentheses, some little extra bit into the parentheses, even if I throw some extra bit into the parentheses, I still get back the original x. Like, even though the original x is different now, it has an extra term in the parentheses. When I differentiate it twice, I get back itself times omega squared times the negative sign. So what I'm saying is, okay, what we're saying here is, wait a minute. Even if I throw an extra term into the cosine parentheses, that doesn't, it changes the function, but it doesn't apparently change the fact that the function, this more complicated function, still satisfies our original differential equation for harmonic oscillation. Apparently, like, we've been saying the solution is cosine omega t. I'm saying, wait, even if we throw in an extra number, we make a cosine omega t plus pi over 2, that's still a solution. In other words, we didn't have to assume that it was omega t plus 0. It could have been omega t plus something. And still, when we take two derivatives, according to the way chain rule works, we get back the original function. So what I'm saying is, this whole time that we've been saying our solution is x equals x naught omega, sorry, this whole time we've been saying that the equation of motion for an oscillator is x equals x naught cosine omega t, or y equals y naught cosine omega t, or y equals a cosine omega t. That's what we've been saying. I'm now saying, you know what? That was actually just a specific solution. We've been picturing x equals x naught cosine omega t plus 0. But if we step back and think about it, we don't have to assume that it's plus 0. In fact, we could be more general. We could put any constant there we want add into parentheses, and we still apparently are describing a simple harmonic oscillator. What I'm saying is this: in general, Okay, with 8 minutes left, here's what I'm saying. I'm saying that actually, well, I'm expanding. I'm making more general now, a conclusion we came to 2 days ago. I'm saying actually harmonic oscillators can be described by a more general equation, A cosine omega t plus some term. That term, that we're going to, the symbol we're going to use for that term from now on is the lowercase Greek letter phi. And we're going to, and phi stands for phase constant. We can put a phase constant into that description and it still captures a harmonic oscillator. Now, what is it doing physically? What does it mean? Very quickly, because I do know that we're running out of time. What I'm saying is that term, that phi, that extra number, like I just use pi over 2 as an example, but it could be any number. You could put a number in that parentheses. And what does that number stand for? What does that number designate? It's a head start or a delay with respect to cycle. So for example, when that number is 0, that means there's no head start or delay in the cycle. It means we're starting our stopwatches at the most obvious time, right when the object, the oscillator, is at amplitude position, at its maximum displacement from equilibrium. It's like that's the natural, most convenient thing to do. But let's say this thing's been oscillating for a while, and we don't start our stopwatch right at the beginning. We start our stopwatch when the thing is already a pi over 2 radians into its cycle. Like we're not taking the cosine, like when t equals 0, we plug in 0 for t, there's still that pi over 2 thing sitting in the parentheses, meaning that we started our stopwatches a pi over 2 radians into the cycle. A cycle is 2 pi radians. So it means we started our stopwatches a quarter of the way into the cycle, meaning we started timing when this thing was already at equilibrium position rather than an endpoint, right? And if that term had been pi rather than pi over 2, it would mean that we started when the thing was on the negative side. You follow what I'm saying? That phase constant term, it's a constant term, but it's like an initial place in the cycle, a head start or a delay. And it helps even further specify our description of a harmonic oscillator. Now, you might ask very reasonably, why would we ever use this? Like, why isn't it always best just to start measuring an oscillator at the endpoint position? Yes, it is most convenient to start measuring an oscillator when it's at its amplitude position. And if we only have one oscillator, then that is always the best thing to do. And there's really no need for this, which is why up until now, we've just been assuming that phi equals 0. But, and I know we have 3 minutes left, and I won't go past, but in the 3 minutes we have left, let me try to at least begin relating this back to your lab. The reason that phi would ever come up, the reason we'd ever care about phi, is if we ever had more than one oscillator. Say we had many, many oscillators. Imagine, and so this is the last page I'm going to write, but just imagine this. Okay, we have 1 minute left, but imagine, just very briefly, with 1 minute, imagine taking a whole bunch of identical vertical oscillators and lining them up, arranging them on a horizontal axis. Imagine putting a whole bunch of vertical oscillators that are all identical and setting them up on an x-axis, and letting them all go and are oscillating at the same rates, but staggering them in phase, allowing the first one to go like from its endpoint, its amplitude position, allowing the next one to start from its equilibrium position, while the next one starts from amplitude on the other side. Imagine staggering them so that each one is out of phase from the last one by a constant amount. Imagine staggering them in phase by a constant phase amount. So if we have multiple oscillators, but all staggered in phase by a constant amount, you know what we would have? We would see a wave pulse, right? We would see each one going cosine in time. But if we step back and look, we would see a cosine in space. And as they all went up and down like this and up and down like this, we would see crests of a wave going across horizontally and troughs of a wave going across horizontally, right? What I'm saying is, this is what you made in the lab 2 days ago. This is what you saw in the lab. A wave pulse is a collection of identical time oscillators, all staggered in phase space. I'll let that sink in. We'll get back to that on Monday, obviously, but just that, and it can all be captured with one equation. That's ultimately what you're seeing in the lab. But okay, I'll leave it at that for the moment. You've been very patient. I'll hear more. Tell me more about the lab if you want, text me or whatever, but thank you guys for being so you. Okay, see you. Thank you. Thank you, guys. Thank you.